Okay, hello everyone, and today I'm going to introduce the internal waves and how they mix different layers of water vertically in the Arctic Ocean. But I think this topic is horrible. So me personally love to call it, oh my god, the sea mountains are making heat transporting from bottom to top. And it is going to be about the heat and the internal waves. So this is the map of the Arctic Ocean. It's freezing cold, but thanks for the currents, there's always some warm water that flows from the south, the Atlantic Ocean, into it. And it will bring this amount of heat into it every year. So once the warm water enters the Arctic Ocean, it will sit under the cold water and the sea ice level like this. And then there is internal waves. Internal waves in this presentation will be directly connected to the waves that will mix water vertically. And the internal waves all over the world have kind of the similar patterns. For example, the internal waves in the Atlantic Ocean and the internal waves in the Pacific Ocean should have like quite the same patterns, feature, energy sort of stuff. So if the internal waves in the Arctic Ocean also have that kind of pattern, it will mix two layers of water and make the warm water transporting upward. And this amount of heat will also transporting upward. Well, I know a lot of you guys have no concept of how many this heat is. So what if I say it actually equals to 12 million gallons of boiling Knorr soup? And the internal wave energy in normal cases will not be lesser than the Panasonic blender. In this case, if this happened and that amount of heat actually transporting from the warm layer to the sea ice level, the sea ice will be all melt at the Saturday morning. But look at the Arctic, it is absolutely not the case. Even though polar bears might not be agree with it. But this actually shows why is it so important to study the heat transfer of that amount of heat in the Arctic Ocean, because if that can melt all of the sea ice, if one mechanism goes wrong, it could cause chaos. And today we're going to focus on the internal waves. So the scientists used to make this assumption that there is almost no stir caused by the internal waves in the Arctic Ocean, that they actually do some fancy math and found that the internal wave energy in the Arctic Ocean is actually pretty low. So they think that the Arctic Ocean is a pool of dead water, and the heat transfer caused by the internal waves can be ignored. Well, if this the real case, I can end my presentation here, but unfortunately, it's not. And my job of today is to prove that this is wrong. So if you look at the previous study, you can easily find out that there was almost no study on rough topography. So if a tide of water flows through a flat area, nothing will happen. But if there is some sort of topography changes, for example, like a mountain under the sea, the water will not be able to flow straight. Instead, it will flow like this. And by this, we can see there's some vertical velocity. And vertical velocity is the evidence of the internal waves. So the internal waves will not only cause vertical velocity, but also heat flux or heat transfer that I just mentioned earlier. And in this case, it's also heat loss of warm water. Heat flux is just a more fancy way to say it. And they can be calculated by these two formulas. So in this formula, at the left side, you can see K, and it is directly connected to the internal waves. It shows how well the water mixed. So the greater number, the better the water mix. And then there is shear, which is vertical velocity, and then n square, which is the n square that everyone knows. And then for this one, it's heat flux. It can be calculated by some oceanic constants times K times temperature gradient. In the case of the Arctic Ocean, it's 1.5 degrees Celsius per 100 meters. And then there is area. So by looking through this, we will be able to know what kind of data should we look for. They are velocity profiles and n square. And because I think if we go through all of these will be too much for you guys and also me in 10 minutes. So I will just compute it out into K. So here is our study area. It calls the frame rate. And these are the contour line of it. You can see in here, we have something that is rough. There are some intense topography changes. And in here, this is horrible. The topography is like more flat. So these will be the locations that we're going to look at by looking through the archive data of these two cruises. So first, in here, this is the K value, and this is the topography profiles. You can see the K value has the maximum number in here at the Urmac, where the contour line has the greatest density in this area. And then the K value has the minimum in here, which is the flattest area. And move to here, you can see the K value has the greatest number in here and has the minimum at the plane, like here. And for the last one, you can see the K volume has the maximum at the ridge and the minimum at the plane. So the red area is the areas that have the greater K volume and also the rough area. And the flat area is the place that have lesser K volume and also the flatter area, which means our hypothesis of sea mountain is proven. So if you look through those figures carefully, you can easily notice that the similar topography means they have similar Ks, which means we can apply the K volume to both, like we can apply the rough K volume to all of the rough area in the Arctic, and also the flat area has the same patterns. If you forget the K number, well, let me show you. The K number at the rough area is about this amount, and at the flat area is about this amount. They are about 100 times away, which means we can ignore the K volume at the flat area, only focus on the K volume at the rough area, and apply it to the whole Arctic Ocean. That me make it black and white, just like my life. So you can see the red area is the place that have rough topography, which is about 30% of Arctic, and make the total area of today this amount. And now we finally have all of our data. We can try to calculate the heat flux. It can be suggested by some oceanic constants times K times temperature gradient times A. Make the final heat flux 9 terawatts. And this may be the heat flux of Atlantic warm water caused by the internal waves in the Arctic Ocean. And 9 terawatts is actually equals to 5 million gallons of canola soup. And if this happened, if that kind of heat actually mixing upward, it's not even neglectable. Which means if we want to do something like, for example, climate modeling, we have to count the internal waves in, because it actually making this amount of heat transferred, and it will affect the sea ice level pretty much. But we also need to remember that because of this amount of heat only comes from 30% of the Arctic, it's probably not the main, because there's also the rest of 70%. There must be some more mechanism going on in there. So, in conclusion, today we're challenging the old view of the Arctic Ocean is just a pool of stagnant water by looking through the internal waves in the different area, different topography area, and found out that even though the internal wave energy in the flat area is pretty low, the internal wave energy in the rough area can cause unnegligible mixing. And that is about 9 terawatts of heat flux. So the Arctic Ocean is not a pool of stagnant water. And the internal wave energy shouldn't be ignored if you want to do some climate modeling or stuff. And that is for today.